Section 3.5 is on the derivative of a to the x and log base a of x. So the derivative of a to the x is ln of a times a to the x. So you take the natural log of the base number, and then you multiply it by the original function. So to differentiate, y equals 2 to the x, we would get y prime equals, you have ln of the base, which is a 2, times the original, which is 2 to the x. Same idea goes for the second one. We take the ln of the base, which is 1.4, times the original, or 1.4 to the x. And for the third one, we have ln of 3 times 3 to the 2x. And you want to make sure you take the derivative of the exponent, which is 2. So what we'll end up getting is 2 ln of 3 times 3 to the 2x. Let's go ahead and try the second set. Very similar to the first set. So when I differentiate 5 to the x, I get ln of 5 times the original, 5 to the x. When I differentiate 4 to the x, I get ln of 4 times 4 to the x. And for the last one, I would end up with ln of 4.3 times 4.3 to the x. Theorem 13 says that the natural log of a is just the limit as h approaches 0 of a to the h minus 1 all over h. The derivative of log base a of x is 1 over the natural log of a times 1 over x. So you're taking the natural log of that base of the log and you're putting it in the denominator, and then you're taking 1 over the bigger number in your logarithm. So for example 3, when we take the derivative, we end up with 1 over ln, and it's the base number, which is 8, times 1 over whatever you're plugging into your function, which in this case was an x. And you could simplify this as 1 over x ln of 8. Let's try the next one. When I take the derivative, if there's not a base that's written, it's a common log, which means it's ln of 10 times 1 over what we plugged into it, which was x. And again, you can simplify this a little bit. That's 1 over x ln of 10. Let's try the third one. We're getting a little bit trickier. So f prime of x, we're still doing 1 over the ln of the base number, which is 3. And then we take 1 over whatever we plugged in, but we're going to utilize the chain rule. And so we need to take the derivative of the inside, which in this case is 2x. And so we can simplify this a little bit. We have a 2x on top, all over an ln of 3 and an x squared plus 1. For part D, we're going to use the product rule. So our first times the derivative of the second, and that's where we're going to use our new definition. That's 1 over ln of 5 times 1 over x plus the second log base 5 of x times the derivative of the first. And so we can simplify a little bit. This x cubed and the x down here will cancel, and we're left with an x squared on top. And so what we have is x squared on top over ln of 5 plus 3x squared times log base 5 of x. Let's go ahead and try example number 4. Very similar. So y prime is going to become 1 over ln of the base, or ln of 2, times 1 over whatever we're plugging in, which in this case is x. And so we can simplify that to be 1 over x ln of 2. For the second part, this -7 is kind of just hanging out up front. And then we're going to follow the same rules we have been. This is 1 over ln. Again, we have that common base, so that's 10 times 1 over x. And so we can simplify this to be -7 over x ln of 10. For part C, we're going to use the product rule. So the first times the derivative of the second. So x to the 6 times ln of 10 times 1 over x plus the second times the derivative of the first, which is 6x to the 5th. So just like in the example previous, the x and the x to the 6 can simplify, which gives me x to the 5th. And so we actually have x to the 5th over ln of 10 plus 6x to the 5th times log x. And so we could actually factor out an x to the 5th because it's present in both pieces. And what I have left over is 1 over ln of 10 plus 6 log x. And for the last one, y prime is going to be 1 over ln of 8 times 1 over x cubed minus 7. But we got to use the chain rule and find the derivative of that inside piece. So that would be 3x squared. So what we get as a final answer is 3x squared over ln of 8 times x cubed minus 7.